Here we are at the calculus block. Earlier in the course, we promised to give you a technique for finding good rearrangements for solving equations by formula iteration. And that's what we're going to do in this programme. We're going to apply the technique to two equations. The first one comes from this problem. Here we have a circular field, and the goat grazing in it is tethered at this point on the circumference. The problem is to find out when the goat can graze exactly half the field. Solving this goat problem is going to lead us to a new technique for finding rearrangements. So how do you get started?
Here's a model which will help us to visualize the problem. This circle represents the field. The goat is here, tethered to the edge of the field here. Now, if I make the tether this long, then the area that the goat can graze is this much, with the boundary drawn out when the tether is taut, and that's obviously less than half the field. On the other hand, if I make the tether this long, then the area that the goat can graze is this much, which is obviously more than half. Now, somewhere in between these two, there'll be a point where the goat can graze exactly half the area of the field. Now let's see what happens as we vary the length of the tether. Here is the field. If the length of the tether is 0, the goat can't graze. As the length of the tether increases, the area grazed increases. When the tether is this long, the whole field is grazed. Now reducing the length of the tether again reduces the area. For some length of tether, exactly half the area will be grazed. If we had an expression giving the area grazed in terms of the length of the tether, that's this distance, then we could put that equal to half the area of the field, and that would be the equation we need to solve. Unfortunately, this turns out to be a horrible equation. It's easier if we express this area in terms of this angle. That one there. And then calculate the length of the tether from this angle. Now let's see how our problem looks starting from the angle. Here's the angle. At this point, the angle is pi, and the area the goat can graze is 0. Now it's a decrease in angle, which produces an increase in area. And when the angle is 0, then the goat can reach the whole field. So when we get an equation for the angle, it'll have a solution between 0 and pi. And that equation will have to connect the radius of this circle, r, and this angle, x. Now let's take stock of where we've got to. Anne?
Let me do that using the strategy from the first TV programme of the course. There, you used this framework for tackling problems, beginning with stating the problem and going all the way round to interpreting the solution. Well, the first thing to do is to state the problem. We've done that. It's what's the length of the tether? And next, we have to put in some symbols. We've chosen r for the radius of the field, a for the length of the tether, and x for the angle. And the next thing to do is to state the problem as an equation. And that's what Bob's going to do next.
To get an equation, we need an expression for this area to put equal to half the area of the field. And in the pre-program work, the area was split up like this. First this piece. And after a good deal of manipulation, we found that its area was that much, x plus x cos x, all multiplied by r squared. Next, this piece. Again, after some manipulation, we found that this area was pi minus x minus sine x, again all multiplied by r squared. Finally, putting these two pieces together gives us the whole area that the goat grazes, and adding these two expressions together gives us pi plus x cos x minus sine x, all multiplied by r squared for the area grazed. Now, if we put this equal to half the area of the field, that's a half pi r squared, we get this equation. X cos x minus sine x plus pi by 2 equals 0. And that's what we've got to solve. Now, to save having to say this lot time and time again, we'll call it f of x. So we're trying to solve the equation f of x equals 0, where f of x is this expression.
So this is the equation we want to solve. And the only way I know to solve it is to do it numerically. Say by finding a rearrangement of the equation for formula iteration. And that's what this programme is about, how to find a reliable rearrangement for formula iteration. Well, the first thing I want to know is what this function f of x looks like. We've plotted it here between minus 10 and 10. There are horizontal tangents here where the derivative is 0. It crosses the x-axis in several places. We want the point between 0 and pi. That's this one. So the expression is positive here at 0, and by the time we get to 3, it's negative. You don't need the graph to tell you that. You could check that by tabulating the function. However, the graph does tell us that there's a solution here near 2. How accurately shall we find that solution? We can get it as accurately as we want. Let's do it to 4 decimal places.
Bisection will do that for us. Starting with 0.3, it takes 16 cycles to get us 1.9057. That's the answer to 4 decimal places. At the start of this program, though, we promised you a really good rearrangement for formula iteration, and that's what we've got here. If we start at 1.5, that's the midpoint of 0.3, we get the solution in 4 iterations. And again, it's 1.9057, the same result. But what is this answer? Well, it's the value of x, the angle in radians, that we need to finish off the goat problem.
We've solved the equation numerically, and we've got x is equal to 1.9057, just less than 2. But x is the angle, and we want a, the length of the tether. So, to interpret the solution, we need to substitute the value for x into this expression for the length of the tether. And we get this much times the radius of the field. So the length of the tether is about 1.16 times the radius of the field. Well, that solved our original problem, but what was the iteration formula we used?
Actually, it was this. It's xn plus 1 equals xn minus this complicated expression with sines and coses all over the place. It may not look much like a rearrangement, but it is. Let's check that. We take off the subscripts, then these x's cancel. Now multiply through by the denominator, and we end up with our original equation for x.
OK, so this does come from a rearrangement. But what's so good about it? You've seen that it converged to this solution more rapidly than most of the formula iteration you've done before. Is that all there is to it? No. We can also use the same iteration formula, without any changes, to find other solutions. This one, for instance. For a starting value, let's take minus 1, 2, 3, 4, minus 4.5. That's a reasonable first approximation. So let's see what happens with a starting value of minus 4.5. We get this solution, minus 4.8323, after 4 iterations. So the same formula gives us more than one solution, and quickly. So although the formula is complicated, You don't have to use it very often, and you don't have to find another rearrangement for the other solution. So it looks very useful. Now, how did we get it?
Let's look carefully at the bits of this rearrangement. It's xn plus 1 equals xn minus this lot. So its form is xn plus 1 equals xn minus a quotient. Now, what about this expression? What is it? Well, the top line is recognisable. If we look at f of x, this top line is this with xn instead of x. So this top line is f of xn. And you've also seen this bottom line before. It's just the value of the derivative, f dashed at xn. So this bottom line here is f dashed of xn. So the formula is xn plus 1 equals xn minus the y value at xn divided by the slope of the tangent at xn. Now, to see what this iteration does, we're going to look at it graphically. And to do so, it's useful to rewrite this expression in a different form. By taking this across and this bit across, we get this expression. We get f of xn over f dashed of xn is xn minus xn plus 1. Now, if we multiply through by this denominator and then divide by this expression, we get an expression for f dashed of xn. We get f of xn divided by xn minus xn plus 1 for f dashed of xn. Here's a sketch of part of the graph of f with an approximation xn and the next one. Let's take another look at the expression for f dashed of xn. The numerator is this term, f of xn, and that's just this distance, the y value at xn. What about the denominator? Well, that's just the difference between successive approximations, this distance. So the expression we've got for f dashed is the same as this distance divided by this one. But that's the gradient of this line, which must mean that this line is the tangent to the curve at xn. Right, this is what's going on. Here's xn, and here's xn plus 1, and this is the tangent to the curve at xn. And each step in the iteration consists of going from the current approximation vertically to the curve, along the tangent until we hit the x-axis, and that's the next approximation. Then we repeat, vertically to the curve, along the tangent to the x-axis, vertically to the curve, along the tangent to the x-axis, and so on. And you can see it homing in on the solution.
So that was what was happening for our goat function. But in fact, this could be the graph of any function, and the argument applies equally well for any function f of x is equal to 0. This iteration formula, xn plus 1 equals xn minus f of xn over f dashed of xn, works for any function, and it's called the Newton-Raphson iteration formula, after Messrs Newton and Raphson. It is an iteration formula because its xn plus 1 is some function of xn. And as you saw in the goat problem, it comes from a rearrangement. Newton-Raphson is a very good, useful technique because it gives a way of writing down an iteration formula for any equation f of x equals 0. It normally converges quickly, and given an appropriate starting value, will give any solution. We'll pursue why it's good later in the block. But how would you use Newton-Raphson to solve an equation if you didn't even know what the graph looked like? In fact, how could you work out the sort of problem you're likely to get in practice?
If you don't know what the graph looks like, you don't immediately know where the solutions are, so you don't know how to choose appropriate first approximations. Now, let's look at an example, a cubic equation. F of x equals this lot equals naught. First, we need to locate the solutions, and we can do that by tabulating the function. Well, I've already done that here. And we can see that the sign of f of x changes from negative at -3 to positive at -2. So there is a solution in there. That is, there's a solution in the interval -3, -2. Now, if we look along, we can see that it changes from positive at 0 to negative at 1. So there's another solution in there. That's in the interval 0, 1. And finally, it changes from negative at 2 to positive at 3. So there's another solution in there. That's in the interval 2, 3. Now, I'm going to concentrate on the solution in this interval. That's in -3, -2. Right. Now we need the Newton-Raphson formula. We know that it's xn plus 1 equals xn minus, and now I need f of xn divided by f dashed of xn. Well, f of xn is all right. That's just xn cubed minus xn squared minus 5xn, and finally plus 3. But for this, I need f dashed of xn, so I'd better work out f dashed of x. Well, that's all right. X cubed gives me 3x squared. Then I've got minus 2x from this, minus 5 from that, and nothing from the last term. So f dashed of xn is 3xn squared minus 2xn minus 5. And that's my Newton-Raphson iteration formula. Now, this formula will find all three solutions, and after the program we're going to ask you to do just that. But I'm going to find the solution between -3 and -2. So I'll take as my starting value x1 equals -2.5. Now, I'm going to use my calculator, and this iteration formula isn't in quite the right form for that. These expressions need to be nested. So I'll write the formula like this. Xn plus 1 equals xn minus, and now I'll nest these. Right. I start with xn, and then put in the coefficient of the next term, that's -1, multiply the lot by xn, bring in the next coefficient, -5, multiply that whole lot by xn, and finally add the 3. Same for the bottom line, 3 times xn to start with, then the next coefficient is -2, multiply that lot by xn, and then finally -5. So when I do the calculation, I'm going to take the current approximation, and I'm going to work out this divided by this bit, and then subtract it from my current approximation. Right, now I said I would start with x1 equals 2.5, so let's do that. 2.5 minus, and store that. Now, in order to work this out, I've got to open these brackets. So I open 3 brackets, take my xn minus 1, close a bracket, multiply by the xn, which is in memory, subtract 5, close another bracket, multiply by xn again, add 3, and that is my top line. Now I have to divide that by, open enough brackets, 3 times my value of xn in memory, subtract 2, close the bracket, multiply by xn, subtract 5, that's the bottom line, complete the division, then subtract that from my current approximation. That gives me my next value, x2 equals minus 2.16. Then I store that and start all over again. Now, if I repeat that, what I get are these values. And you see it converges quite quickly to a solution of minus 2.0861 to 4 decimal places. And I could find the other two solutions using exactly the same formula and appropriate starting values.
We've been claiming that Newton-Raphson will find any solution. It'll do it for Bob's cubic, and it did it for our goat function. We've found these two solutions. But are there any snags? Unfortunately, yes. Let's have a look at what happens when x equals 0.5, which is nearer to this solution than any of the others. So you'd expect it to converge to about 1.9057. It's converged all right, but to 7.9264. That's this solution. So what's gone wrong? Here's 0.5, vertically up to the curve, and along the tangent. Like that. But that's taken us away from the solution and goes away over here to this solution. So a starting value of 0.5 is bad for this solution. The problem is that the tangent is too shallow, and the shallower the tangent, the worse the effect. We had a sketch, so we could avoid that choice of starting value. If you don't have a sketch, what would you do to spot this? The slope of the tangent is given by f dashed. Look at the formula. Here's f dashed on the bottom. And a shallow tangent means that f dashed of xn is close to 0. So this quotient is likely to be large, which means that xn plus 1 will be a long way from xn. So we know we've got to avoid starting values where the derivative is close to 0.
But don't let that put you off. It is a very good method, but you don't need to take that from me. We could check by using what we did in Block 2, Unit 4, where we investigated when iterations worked out. Now that would involve differentiating this whole expression. But to do that differentiation, we'd have to differentiate this quotient. And the technique for doing that is in the next section of this unit.
So, what have you seen in this programme? You've seen a method, the Newton-Raphson method, for finding iteration formulas. And it's a method that works everywhere except near horizontal tangents. So you need to know what the graph looks like. And in the next television programme, you're going to find out how calculus can help you sketch graphs. Now, here's a final thought. What would happen if the goat's field were square?